In advanced manufacturing, the physical performance of a material is rarely uniform. When a solid sheet of metal is stamped or bent under heavy pressure, its tendency to stretch, buckle, or tear is highly directional, a property known as anisotropy. This macroscopic directionality is dictated by a hidden architecture, orientation mapping. Engineers cannot rely on direct observation alone. They must bridge the scale gap by building a rigorous, three-stage mathematical pipeline. This diagram illustrates that pipeline. The first stage requires translating physical surface observations, specifically the Miller indices of a crystal plane, into an algebraic framework. The final stage takes that algebra and converts it into a sequence of mechanical rotations, codified as Bungee-Euler angles. Without calculating these precise rotational offsets, engineers cannot predict failures, a torn deep-drawn autobody, or a snapped forged turbine blade. Mastering this specific mathematical pipeline is the only reliable way to control material behavior from the atomic level up. We begin the deduction by translating physical geometric observations into absolute mathematical constraints. This graphic breaks down the first step. Normalizing the physical intercepts of a crystal plane derives our first unit vector, the plane normal, n hat, pointing perpendicular to the surface. Concurrently, normalizing the directional indices gives us the second unit vector, b hat, lying flat along the plane. To map orientation in 3 dimensions, we require a full coordinate system, which dictates an orthogonal basis of 3 mutually perpendicular axes. Here we see the mathematical operation to secure that third axis. Taking the cross product of the normal and direction vectors calculates the trajectory of the transverse vector, t hat. Together, these 3 unit vectors complete our 3-dimensional space, forming a rigid framework representing the microscopic crystal's internal axes. The algebraic step binds these vectors together. By aligning b hat, t hat, and n hat as individual column vectors, we assemble a singular 3x3 array known as the orientation matrix, A. The columns of this matrix represent the microscopic crystal axes, translated into the macroscopic sample frame. Matrix A provides the first complete algebraic translation of the physical crystal geometry, fixing the orientation within a computable array. While Matrix A defines a single orientation, international crystallography standards require a uniform way to describe the distribution of orientations across massive datasets. Representing every grain with a full matrix is redundant. Instead, software protocols favor a more compact 3-parameter set. This is the Bungee-Euler framework. It replaces the singular matrix mapping with 3 specific sequential mechanical rotations. These operations are designed to physically spin the static sample frame through space until it locks into alignment with the internal crystal frame. The sequence begins with the first rotation, denoted as phi 1. This diagram visualizes the action. The entire crystal coordinate frame is rotated around the original specimen z-axis, aligning the x-axis directly toward the desired heading of the crystal plane. While the physical action is mechanical, the software executes it using this mathematical operator, matrix G phi 1. At this stage, the horizontal azimuth is established, but the vertical alignment of the plane is still disconnected. This first rotation establishes a base heading, but necessitates a subsequent tilt to align the plane's true normal. We proceed to the second sequential rotation step, denoted as capital phi. This visual dictates a vital computational rule. This tilt does not occur around the original static sample axis. The frame tilts around the newly shifted x' axis, pushing the normal vector into alignment with the specimen z-axis. This specific tilt is executed mathematically by the G-phi operator matrix. The third and final rotation is phi 2. It executes a spin around the newly created z" axis, locking the crystallographic orientation into its final physical alignment. We now possess 3 distinct mathematical operators. To execute mapping efficiently, we must unify them into a single command. This equation defines the composite transformation pipeline. When tracking coordinate vectors, computational rules dictate that matrix multiplication must be applied from right to left. Multiplying those 3 individual step matrices yields this master 3x3 composite tensor, defined universally as lowercase g. This master tensor defines the exact computational offset required to conclusively locate any physical crystal within a bulk material, finalizing our derivation. While the underlying mathematics allow for infinite rotational possibilities, physical reality imposes strict geometric limits. Highly ordered structures, like cubic metals, possess intrinsic lattice symmetry. If you rotate a microscopic cube 90 degrees, its structure appears identical to its original state. Because of this geometric overlap, certain rotations produce redundant orientation data. We do not need to process a full 360-degree sphere of calculations for every material. This chart categorizes computational limits using Laue classes. Notice the cubic system row. Angles are constrained to 90 or 180 degrees. Compare that to triclinic materials. Lacking internal symmetry, they require a full 360 degrees of rotation to locate a unique position. Identifying and applying these intrinsic symmetry boundaries shrinks the mathematical space, reducing the required processing power to map millions of individual grains. That bounded computational volume is visualized as a framework known as Euler space. Here, the angular limits of phi1, capital Phi, and phi2 construct the axes of the cube. Within this specific geometry, every individual coordinate point represents one unique, non-redundant crystal orientation. Viewing the vibrant output of a modern electron backscatter diffraction scan, you see constrained Euler space data mapped onto a physical grid. That final map is the direct result of this pipeline. We standardized physical surface observations into strict orthogonal orientation matrices. We then decomposed those matrices into the sequential mechanical rotations of Bungee Euler angles, unifying them computationally. This mathematical pipeline provides the mechanism for translating a material's crystalline state into the variables used in predictive manufacturing simulations. It is the necessary framework for connecting microscopic surface observations to the engineering of predictable, high-performance components.